Today I want to talk to you about the binomial theorem and the binomial distribution, two seemingly unrelated parts of the content, but of course if they have the same name, they can't be unrelated. So actually this is going to be two videos. This is the first one, which is just going to be about the binomial theorem, and this is appropriate for students either in the standard level course or in the high level course, because I'm not going to cover the high level part of the binomial theorem. In the next video, we are going to be exploring the connections between this and the binomial distribution, but we're also going to talk about some other things. So I think that the second video is going to be more appropriate for students taking only the high level course. Of course, if you're taking standard level but you want to watch it, that's also fine. Before we begin, I want to propose an exercise that may sound a little bit silly for you, but it's going to be helpful, so pick up a piece of paper and copy the picture. The exercise is that you are supposed to complete the pattern in the following way. Every time that you see two numbers side by side, you add them up and write the answer in the next line, sort of between them. So 2 plus 1 is equals 3, 3 plus 1 is 4, 3 plus 3 is 6. Just continue going on in this way. Pause the video and then compare your answers to mine. Just have one more line here to give you an extra chance to actually pause the video and do this yourself. So in case I explain the pattern too quickly, here it is again. So it's like 6 plus 4 is 10, 4 plus 1 is 5, and along both sides of the triangle, you're just going to have this row of ones. All right, so hopefully we have all the same numbers. I have stopped on the line of the number 8, but of course this is an infinite thing, right? You can keep going on for as long as you have the patience to do so. And this is a very common pattern. It has a name. This is called Pascal's triangle. I am going to have to erase it now to continue the video, but of course you've done it on paper, so keep it close to you. You're going to want to compare it to something else later. So here is the second exercise, and this is also very good just as an exercise without even trying to lead up to any content, because you're going to have to practice your algebraic manipulation skills, right? So there are common mistakes that people do when they're not paying attention to these things. So we're going to want to take x plus y to the power of various things. The list is going to keep going on, but looking at just these for now, x plus y to the power of 0 obviously is 1, just like anything to the power of 0. X plus y to the power of 1 is just x plus y. And x plus y to the power of 2 is a very common mistake that a lot of people just write down x squared plus y squared, right? Of course, that is not correct, because this thing to the power of 2 means that it's the thing times itself. So we're going to have to use distributive. So we begin by multiplying x times x equals x squared. But then we have to do the other ones, right? And then you combine the like terms here in the last step. This is 2xy, which is something that a lot of people actually know by heart. It's called a special product. X plus y to the power of 2 is equal to x squared plus 2xy plus y squared. I'm going to erase this part now and just leave the answer here because I want to do more lines. The next one that I want you to do is x plus y to the power of 3, which is not something that a lot of people know by heart. And I'm not suggesting that you should, okay? If you memorize it, fine, but you don't have to. What I really want you to do is to think about this power of 3 as the repeated multiplication that it is, but don't write out the x plus y 3 times. Instead, you're going to write it one time and then multiplying by the power of 2 that you already had before, like this. So it's the repeated multiplication of x plus y times itself 3 times, but one of those times is here and the other two are here. But this result we already have from the previous line, which is equal to this. Therefore, I have copied that down here. And now I want to do the distributive again, but with these terms. It's like this, right? Every term in that factor needs to be multiplied by every term in this factor. I've put some of them in green and others in orange to see if we can still visualize all of them. But the important thing is that I want you to pause the video and write out all 6 things that you're going to get now. So it ends up looking like this. The first 3 are the ones that came from the green part that is multiplying by this x. The orange ones came from these 3 terms being multiplied by this y. So for example, the middle one here, it's x times 2xy, which becomes 2x squared, because there's another x coming from over there, times the y. So all of these multiplications have been done. And now you need to combine the like terms, because, for example, I have x squared y here, but I also have x squared y here. So I actually have 3 of them, 2 over there and 1 over here. Now I've color-coded them a different way just to show what are the like terms that I'm combining. So this one and this one became this red one, and the 2 purple ones are also the same kind of term, so they become this one. And this line over here is the final answer for x plus y to the power of 3. So again, I'm going to erase all of these lines and just put the final answer here. And now I want you to pause the video and keep going with this exercise in the exact same way. It's just practice of algebraic skills and distributive. So now you want x plus y to the power of 4, which means that you want x plus y times x plus y to the power of 3, which is the previous one that we've just done. So you're going to get another factor of x plus y and multiply by this thing here, which now has 4 terms. You're going to distribute and you're going to get 8 terms in the end. Combine the like terms and write down the answer here. Then you do it again for power of 5, power of 6. As far as you have the patience to go, pause the video and go do that. When you come back, I'm just going to have all of these 3 answers here. I'm not going to go through the details anymore. Okay, so here are the answers. I'm going to get out of the way so that you can see everything and compare my answers with your answers that you have on your paper. And it may be the case that we have the same terms just in a different order. So keep an eye out for that. So that you don't think you got different answers when they're in fact the same answers. But just so you know, the order in which I chose to write my terms is that I begin with the biggest exponent of x, and then I go down by the exponent of x. So if you look at the last line, it starts with x to the power of 6, and then it has a term with x to the power of 5. The next one is x to the power of 4, 3, 2, 1, and then no x's at all. Okay, so it's convenient to write them down in this order. So have you seen it yet? Have you figured out what the connection is between these 2 exercises that we have just done? There are the same numbers. Look at your Pascal's triangle in your paper. Here, I've circled all the numbers. There are still a few numbers missing because there were a bunch of 1s in the Pascal's triangle, but they are all here, right? This is 1x, 1y, 1x squared. There they are explicitly now. So it's just that when a coefficient of a term is 1, we don't tend to write it down, right? But here they are. So here's the thing. You had more lines in the exercise for Pascal's triangle than you do for this one. I remember I went until 8. This is just 6. So the next part of this exercise is the following. I think we've done enough of practicing distributive now, but I still want to put 2 more lines on this list. I want to put x plus y to the power of 7 and x plus y to the power of 8. But I don't want you to spend all of that time doing all of the distributives now. Now I want you to use this new trick that you've just learned, which is just as much as a lot of people know x plus y to the power of 2 by heart. So when you see that in the middle of a calculation, you don't really have to expand it and do distributive. You can just write this because you know the answer by heart. You probably don't know these other answers by heart, but that doesn't mean that you need to do all of this work explicitly like you did just now. This was an exercise. But in the middle of a question, I hope you can do it faster. And that is the trick, is to remember the Pascal's triangle and to just write out the answer. It's going to be easier right now than if we just ran into x plus y to the power of 7, because we've just written x plus y to the power of 6. So the answer is right here, and you can go ahead adding coefficients. So the first one is going to be 1, as usual, so you're going to start with x to the power of 7. But when you go for the next coefficient, you're just going to write down 1 plus 6, which is 7. And then the coefficient of the next term is going to be 6 plus 15, which is 21. So you go on in this way. Remember to put the terms in this order, okay, with the descending exponents for one of the variables, which in my case I'm doing it with x, and everything will work out fine. So in the middle of a question where you don't have the previous ones written out in front of you, you have a few options. Option 1, you can just write them because it's easier to do it from the top to the bottom. Option 2, instead of writing all of these terms, you can just write down the Pascal's triangle on the side of the page because that is faster to write down. It's just the numbers, just the coefficients without all of the x's and y's. So if you know that you need x plus y to the power of 7, you just take a little bit of paper and write down 7 lines of Pascal's triangle. Then you will have that row of numbers at the bottom. Those are the numbers that you know you need for the expansion that you're looking for, and then you just write down the answer. I think that's the faster way. There you go. Please compare that to your answers to see if you have learned how to do this properly. And guess what? You have just learned the binomial theorem. That is all there is to it. This is the binomial theorem. The only thing is that they wouldn't probably ask you to write down the expansion of x plus y to the power of 8 for a very simple reason. It takes a long time just to write it out, so it's a time waster and it serves no purpose. So instead of that, what they tend to do is to just ask you for one of the coefficients of the expansion. So for example, the exercise here could be find the coefficient of the term x3 y5 in the expansion of x plus y to the power of 8. And then the answer would be 56. But you find it in this exact way. You write down the Pascal's triangle, you pinpoint which of the terms you want, and then that's the answer. It's 56. So in order for them to put that into the formula booklet to help you even more with this, even though it is a simple and small topic, the problem is that it needs to turn into a formula. And when we take that whole process that we've just studied and try to write it in mathematical notation as a formula, I think that that is probably the thing that is confusing to a lot of people and is making you think that this is a complicated topic when it really is not. So let's think about, from the point of view of the people who are writing the formula booklet, how can I put that in the booklet? I can't just put a formula for x plus y to the power of 8 like the one we just did, because 8 is an arbitrary number, right? I want the students who have this booklet available to be able to do that for any number, not just 8. So the first thing that they need to do is to take away that specific number 8 and put a variable in its place. Let's call it n. Anyway, we've learned that this refers to a line in Pascal's triangle, right? And it's always going to start with that 1 from the Pascal's triangle, which in our case is going to be 1 as a coefficient of x to the power of something. And so the first term that I'm going to write down in my formula is x to the power of n. And then I know that the last one is going to be y to the power of n. But before I get there, I need to go through a few things first. And if you're looking at the Pascal's triangle that you still have in your hand because you did that on paper from the first exercise, so you can see a pattern that the next term, the thing that comes after the 1, is this one here, which in this case was 8, but the previous one was 7, 6, 5, 4. So the next one is just going to be n. whatever happens to be the number in the exponent of the binomial is also going to be the coefficient of the next term. And by the way, I just said the word binomial, right? This is where the word comes from. Bi is 2, so here's a 2 term, so this is a binomial that it's putting to a power of n. So here I have n as a coefficient, and this term is going to have x to the power of something and y to the power of something else. This is my second term in my expansion, like the ones that I did explicitly in the previous board. And I mentioned that the order in which it is convenient to write those terms is in descending exponents of x, right? So if the first one is x to the power of n, the second one is x to the power of 1 less than that, so it's n minus 1. And maybe you've noticed that before in the previous examples, that when the exponent of the x is decreasing, the exponent of y is correspondingly increasing. So this one is y to the 0 because there's no y here. This here is y to the 1. The next one is going to be y to the 2. But I still don't know what the coefficient here should be. And actually, I know what the coefficient is the next number in the Pascal's triangle. The only thing that I don't have yet is a name to call it by in order to write my formula. So now is the time when a mathematician creates a name for the thing that he wants to refer to. In the formula booklet, this is called by this notation. You can read it and choose to. I'll talk about the reasons for calling it that a little bit later on. Just know that there are other possible notations that you can write this in. A very common one is this parentheses with a stack of 2 numbers over there. This is just a curiosity at this point because the one that you need to recognize is really the one in the formula booklet, right? So that is the name that we are going to call all of the numbers in Pascal's triangle. And now I want to talk about rows and columns in Pascal's triangle, but it's kind of weird to talk about columns when it's written diagonally like this. So I'm going to erase my triangle and just write it down a little bit shifted like this. So there you go. You can see that there are still the same numbers. If you're writing it out in this format from the beginning, just pay attention who you're adding to who, because now it's like this plus this equals 6. This plus this equals 20. It has to go sideways a little bit. So maybe you should practice doing that. And the more times you just write down the Pascal's triangle from scratch, the more you're going to begin to recognize the numbers because it's always going to be the same numbers. So don't try to memorize the numbers. That's not what I'm suggesting. But I am suggesting that it's a very easy exercise to just pick up a blank piece of paper and write these things down, adding a bunch of pairs of numbers, right? It is a very easy exercise, and it's worth doing sometimes because if you do it over and over again and you start to recognize that it's always the same numbers, if it comes time for your exam and you're doing this and you happen to make a mistake, there's a better chance that you will notice that. Like, this number was never here before. What's this number doing here? So I must have calculated something wrong along the way. So it's something that is worth doing over and over so that you're just very familiar with it, which is different than saying that you should memorize it. So now that I've rewritten it this way, it's easier to talk about rows and columns. I started with row 0 because I want the name of the line to be the same as the number who is here, right? So for this to be row 6, this needs to be row 5, and this is row 2, row 1. The first one needs to be row 0. Now I want to do the same with the columns. So I've started with column 0 as well, okay? And the thing that we were trying to point to a particular number in that table of numbers by our notation, let's pretend that we're talking about n equals 6 right now, just because it's a line that we have here. So we are talking about 6 choose 2, which is supposed to be the number in Pascal's triangle, which is in row 6, column 2. So it's that number over here. And now we have found what we needed. It's a way to refer to the number that comes on the Pascal's triangle line right after the number that is just n itself, where n is the exponent. You see, it's an easy thing, but it's not an easy thing to say, which is where having notation really comes in handy. And now the next one is just going to be the same, right? It's not going to be n choose 2, but it's going to be n choose 3. And I've also followed the pattern in the exponents. So the exponent of x was going down as n minus 1, n minus 2, and minus 3. The exponent of y was going up, like 1, 2, 3. And then I just did plus dot 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 and plus the last term finally, which we mentioned was going to be y to the power of n. So far, so good. So x plus y to the power of n is a sum of many terms. I know that the formula booklet doesn't do that, but I'm going to write that using sigma notation. And if you don't know sigma notation, just ignore it. The important part is going to be the general formula for a specific term that's going to come in here, because like I mentioned, this is the thing that the question is usually asking for. So x plus y to the power of n is a sum of many terms. Each term looks pretty much the same. It starts with a binomial coefficient, which are these numbers that belong in the Pascal's triangle. So it's always going to be n choose something. After the n choose r coefficient comes x to the power of something. And this something, as we can see here, is always n minus a number, where this number is the same as this other number, which is going to be the exponent of y. And it's also the same as this number right here in the binomial coefficient. And that happens again in the other term as well. Look, there's a 3 here, and 3 here. So that happens in all of the terms, and it's going to happen here in the general term as well. There's an r here, so here it's n minus r, and the exponent of y is r as well. There you go, that's the formula. I hope I was able to convince you that it's not as difficult as it looks, because that is what I was trying to do with this process. The next thing that we're going to do is look at a few exercises. Before we go into that, I just want to mention that if you're doing a paper 2 question, then the n choose r numbers can be found in your calculator. I am going to show that at some point during the exercises, and which allows them to work with larger numbers in the questions, okay? We will see examples of that. Okay, so let's begin with 3 exercises here. You will see that they are very similar to each other because, frankly, all of the exercises on this topic are really similar to each other. So the first one is interested in x plus 1 to the power of 7. So instead of x plus y, he has x plus 1, which is going to have the tendency to make things easier because 1 to the power of anything is just 1. In all of those terms that look like this, instead of y, you're just going to have 1. And 1 to the power of r is 1. So you're multiplying by 1 here. You don't need to write this part at all. So it's actually a simpler version of the thing we were mentioning before. In terms of how is he asking this question and how do I recognize this as a binomial theorem question? Well, first of all, every time that you have a binomial to the power of a number, you can already recognize this. I think that the usual way to ask this question would be what I wrote in purple here, which is find the coefficient of the term in x to the power of 5, like other questions here do. But instead, he chose to write out the expansion in terms of some letters here, A, B, and then the next one is not C, it's just 35. So he says x to the power of 7, which we know is the first term, and then the second term is going to be something with x to the power of 6, which he's calling A. The next one is x to the power of 5, but the coefficient is b, and this is the coefficient that he is interested in. He wants to show that b is equal to 21, and b is the coefficient of the term in x5. He did say that the next one is 35, so I think I can find 35 in Pascal's triangle. Yes, 35 is here in the line of the number 7, which is not surprising. So if we are going in a sequence of coefficients there that starts with 1, then a, b, and then it's 35, well, here it is, 1, a, b, and then 35, so b is 21 like we wanted. So I guess that I would write something like this. I would make sure to mention the general term, 7 choose 2, x to the power of 5, 1 to the power of 2, and then show that I know that 7 choose 2 is 21. One of the ways that you can show on a test that 7 choose 2 is 21 is actually by writing this and then marking the 7, the 2, and the 21. It's not the only way. I'll talk more about it in a little bit. Now look how similar the next question is. Again, I have x plus a number. Okay, and this time the number is not 1, it's k, but it's still x plus something, and the exponent is 7 again. He is again interested in the term in x5, which is the same one as in the previous exercise, but he is telling me that it's 63, and well, it was 21 before. 63 is not 21, but luckily at least 63 is 21 times 3, so there's something there, and he's asking me to find k. I've put this question here to show you how he can put some variation into the questions that he's asking you so that it's not always the same question. So these are the usual ways that he can add variation in any sort of exercise. So first one is asking for a coefficient. The second one is giving the coefficient and asking for the k. So the usual variations, right? Instead of giving you this and asking for that, he can give you this and ask for this, or any variation of these things. So I've written here a possible way that I could work this question. Of course, I'm working in very little space, so it's a little bit shorter. But again, I am making sure to tell him that I know what this question is about. This question is about the binomial theorem, so I am writing out the general term of the binomial theorem. Well, this is not the general one, right? It's the one with x to the power of 5, which is the one that I'm interested in. But look at all the things that I'm telling him that I know. If it's 5 here, then it has to be 2 in the other one, because it's going to be 7 minus 5. Or rather, 5 is 7 minus 2, right? So there's a 7 and the 2. I know that 7 choose 2 is the relevant coefficient here. I know that 7 choose 2 is 21, and the rest is just solving an equation. But I want to put something in a wrong box here, because there is a very common mistake that I see, and I want to point it out in case it happens to you as well. And this mistake, as with a lot of other mistakes, is just about the student not reading the question carefully enough. Because here's the thing, the question is telling me that the coefficient is 63. All of these questions are going to revolve around coefficients, because that is the interesting thing about the binomial theorem and Pascal's triangle, which we've just spent a long time talking about. The coefficients are the numbers in the triangle. The coefficients are the numbers that multiply each term in the expansion of the binomial. So it's going to be 63x cubed, not cubed, 63x to the power of 5. But the mistake is when instead of reading what the question is telling you, the question is telling you that the coefficient of x5 is 63, but instead of reading the question, a lot of students just look at this. X to the power of 5 is 63, so they write down x to the power of 5 is 63, and then from there they do a correct move, which is to say that x is the 5th root of 63. This is absolutely wrong. This is just, you didn't read the question. The question did not say that x to the power of 5 is 63. The question said that the coefficient of x to the power of 5 is 63. That is the thing that is 63. So not this. The thing that is equal to 63 is 7 choose 2 times k to the power of 2. And let me tell you why the k to the power of 2 is included as part of the coefficients in this case. It's not just the 7 choose 2 that is the coefficient. The thing is that when we were just exploring the distributive before, we had x plus y to the power of 7, and x and y were both variables. Neither of them were a fixed number. But when he says x plus k, then it implies that x is a variable but k is a number. Pretty much because he's asking you to find it. He's asking you to find the value of k, so it's implied that k has a value. So it's a number, it's not a variable. All of these terms are very important for you to be comfortable with in order to avoid this kind of silly mistake that is just not reading or not understanding the words that are in the question, right? So the k squared here is also a number. So the general term here that came from our previous work in understanding how the binomial theorem works, we know that each term has 3 parts. First is the binomial coefficient, then it's a power of the first thing in the binomial, and then it's a power of the other thing in the binomial. So we wrote all of these 3 parts, but in this particular case for this question, only the middle part included a variable, which was x. The 2 parts, the one on the left and the one on the right, were numbers. So 7 choose 2 is a number, and k squared in this case is also a number because k is not a variable, it is a value. So everything that is a number multiplying x is going to become a coefficient, so the numbers are coefficient, which in this case is 7 choose 2 times k squared. That is the whole coefficient of that term, and that is 63. So then you solve the equation, and k needs to be plus or minus root 3. The third problem on this list is phrased in a more straightforward way. I think this one is the standard one. So find the coefficient of the term in x to the power of 9 in the expansion of x plus 3 to the power of 11. So what are you going to do? You're going to write the term by using what we learned earlier. Okay, so this is the general thing, and this is the one that we want. We still have some blanks to fill in. The exponent of the binomial is 11, so that's n here. We need this n, and this n is 11. But here, the exponent of x, we want it to be 9 because he's talking about x to the power of 9. So if this is 11, then this needs to be 2 here. The r is 2, which means that it goes like 2 here and 2 here. Notice, by the way, that this could also be written like this, with the r as an exponent of the x and the n minus r as the exponent of the 3. There are several explanations that I could give you for why this doesn't matter. One of them is that x plus 3 and 3 plus x is exactly the same thing, so it shouldn't matter if you're going from the left to the right or from the right to the left. The other thing that you can look at is that each line in Pascal's triangle has this symmetry as well. So it's 1, 6, 15 here and 1, 6, 15 over there. So here as well, if you go from left to right or from right to left, it doesn't matter. As long as both exponents in both terms of the binomial are adding up to the total exponent of here, then you're fine. If it's 9 plus 2 or 2 plus 9, it's 11 anyway. But of course, in this case, I wanted to put the 9 on the x because of what the question is asking me to do. Okay, so 11 choose 2 is 55. I found that in the calculator. I'll show you in a minute how to do that. And 3 squared, obviously, is 9. Now 55 times 9 is 495. So you write down the answer. The coefficient that we were looking for is 495. It's the coefficient of x to the power of 9, or the coefficient of the term in x to the power of 9 in that expansion that we were working with. So let me show you quickly in the calculator. This is kind of silly because, of course, every model of calculator is going to do it in a different way. But in case you happen to have the same one as me, which is the TI-84, you go to this menu here, the math button. You're going to go to the right in the probability section, and then here it is, and choose R. Click enter on that. So the 11 comes on the left, and so the 2 comes here. Press enter, and it's 55. Of course, I could have found that 55 in the Pascal's triangle as well, right? The only reason why I chose to go to the calculator was because the line of 11 wasn't here yet. I only wrote up until 7. But come to think of it, it wouldn't take that long to get to the number I wanted anyway, because it was 11 choose 2. Although it's 4 lines away, it's only choosing 2, so I don't need to write another 4 lines. I just want 11 choose 2, which is column 2. So I think I can do it just here. Look, I need 4 lines. The first 4 numbers are ones, as usual. And then the second column is 8, 9, 10, 11. And then the third column, which is column 2, because it started at 0, right? So the next one is the one that I want. 21 plus 7 is 28. 28 plus 8 is 36. 36 plus 9 is 45. And 45 plus 10 is 55. So there's that option as well. All right, so here are 3 more problems for us to solve. The first one says find the constant term in the expansion of that thing to the power of 15. And this is a very common term that they use, constant term. Now, what does constant mean? Constant means something that doesn't change. And what changes in math? Variables change. So if something is constant, that means that it doesn't have a variable. It's just a number. A number doesn't change, like 5. 5 is a constant. Now something like 5x squared is not a constant because it changes depending on the value of the variable x. So in other words, when he asks you for the constant term, he is asking for that term that doesn't have any variable, doesn't have any x, is just a number. As always, I am going to start this by writing the term for that expansion. Notice that the expansion can look a little bit more complicated than the previous ones because it has a fraction, but the procedure that I'm going to use is exactly the same, which is to remember the term in the binomial theorem that I've studied today. So the term looks like this. It's 15 choose something, and then a power of the first term, which is x squared, and a power of the second term, which was the fraction, and the exponents of these 2 terms are respectively 15 minus r and r. Now what I'm going to do is just put those 2 things together, use properties of exponents and fractions, so it becomes this. A power of a power, so 2 times 15 minus r became 30 minus 2r. Again, a power of a power here, so 3r became 3r. And then this is a division, so I am subtracting this 3r from the exponent of the other one, so it becomes 30 minus 2r minus 3r, which is 30 minus 5r. I would have done this regardless of which term he was asking me for, but he is asking me for the constant term, so the term that doesn't have any x. In order for this thing to not have any x, I need this exponent here to be 0. So if 30 minus 5r needs to be 0, you solve that very simple equation, find out that r equals 6. So this is the answer, right? R needs to be 6. So the coefficient that you're looking for is 15 choose 6. This just becomes 1 because it's x to the power of 0. So there you go. The constant term is just 15 choose 6. Of course, either go find it in the Pascal's triangle or type it in your calculator or do something else to find a number. And when I say do something else, what I mean is that you do have this in the formula booklet as well, right? So it is a way to find explicitly the number and choose R. I'm just going to plug in n equals 15 and R equals 6. I think that plugging 15 and 6 into a formula that is given to you, or plugging 15 and 6 into a calculator, is not different at all. Those are just two different versions of the same thing. This you're gonna do if it's paper 1, the calculator you're gonna do if it's paper 2, but there is no difference conceptually between plugging numbers in a formula mindlessly or just having a machine do the calculation for you. Either way, it's fine. It allows us to think about the whole things that are around it and not worry so much about just boring computations. So let's do that once. Let's put 15 and 6 over there. Those exclamation marks in the formula are factorials, right? So a factorial is when you take a number and then multiply by the next smaller number and then multiply it again by the next one, and so on and so forth until you get to 1. For example, 15 factorial is 15 times 14 times 13, and you can't even see the end of that line because it's off camera, but it's not surprising, it keeps going. And then down here I have 6 factorial, which is my R, so it's just 6, 5, 4, 3, 2, 1, then multiplied by the n minus r factorial, and n minus r is 9 because it's 15 minus 6. So the interesting thing is that a lot of this cancels. It looks like a very scary number with a lot of numbers, and frankly this one really is a little bit scary, but there's a lot of cancellations that you should do as well. Starting from the fact that the part that you can't see on the camera, the 9 times 8 times 7 times 6, it is happening at the numerator and at the denominator as well. So it doesn't even matter that we can't see it on the screen because I'm gonna cross them out anyway. So now that part is gone. The thing that remains to me is to see what else I can cancel. For example, 15 is 5 times 3, so I can cancel that. Cancel a 15 from the top with 5 times 3 in the bottom. What else? I have 6 times 2 in the denominator, which is 12, so I'm gonna cancel this 12 with that 12. I've just noticed that I've skipped 11 for some reason. I don't know if you saw that, but there's an 11 there. I still have a 4 in the denominator. It's supposed to cancel out everything, okay? It's not supposed to be a fraction, the final answer in the end, because this is a binomial coefficient. It's 15 choose 6. It is a number in the Pascal's triangle, so it's supposed to be integer. It's not supposed to be a fraction. If in the end you're not able to cancel something, you've either forgotten something or made some other mistake. Because this 4 here, I'm now going to cancel out one of the 2's with the 14, which is going to make this a 7, and the other 2 is going to cancel with that 10, making it 5. And now I'm just going to, in the next line, write down in a very organized way everything that's left, everything that I haven't canceled, which is still kind of an annoying calculation to do, but not that much, right? I can do that. 7 times 13 is 70 plus 21, which is 91. 11 times 5 is 55, so now all that I have to do is 91 times 55. 5005 was the answer to that question there. Anyway, question 5 is asking us the same kind of thing but using a different term, which is why I included it here, because I want you to be familiar with all of the words that are common, right? So instead of asking for the constant term, which is the term that doesn't change because it doesn't have any x, this one is asking us for the term independent of x. So once again, it is the term that doesn't have any x. So once again, I've written the general thing here. It begins with 9 choose r because the exponent is 9. and r is something that I will have to find out. But then I have the first fraction to the power of 9 minus r, and the second fraction to the power of r. Let's be careful because this one is minus instead of plus, so the only thing that changes is that this is a minus here. So it's times minus x over 2 to the power of r. If r happens to be an even number in the end, then that minus is just going to disappear. But if r is odd, then it's not going to disappear, so we have to remember that. The other thing that we should pay attention to in this question that wasn't in the previous one is that this question doesn't have only our binomial that we're going to use the theorem for. It is that multiplied by another fraction that is just sitting there. It's not plus something to the power of anything. It's just 1 over x to the power of 3, which is then going to be multiplied by the binomial, which means that it multiplies by every single term in the binomial. So dividing by x to the power of 3 subtracts 3 from every exponent of x, right? This is a very basic fact about properties of exponents. By the way, we've already used that fact in the previous question right here. So the moral of the story here for this question is that even though he is asking me for the term independent of x, I am not trying to find a term of x to the 0 in this binomial power here. I am trying to find a term of x to the 3, because then that is going to cancel with this x to the 3 here, and that is going to become a constant, which is a term independent of x. So I'm getting out of the way here so that you can see the whole thing. I'm not going to explain every single step in a lot of detail here because it's basically the same thing as we did in the previous exercise. I am just doing a power of a power and then putting the powers together, and in the end this turns out to be the exponent of the general term, which, remember, is the thing that I want to be 3. So I've set that exponent equal to 3, finding out that r needs to be 7. By the way, 7 is an odd number, which means that the coefficient is going to be negative, like we discussed before. So now I've just plugged in r equals 7 into the previous formula. The negative is here, and I have to figure out what is 9 choose 7. Now remember I talked about the symmetry of the Pascal's triangle, where reading it from the left to the right is the same as reading it from the right to the left, and the smaller numbers can be easier to work with. So 9 choose 7, same thing as 9 choose 2. That's the one that you should try to put in the formula, or write the triangle, or whatever you choose to do. Going with the formula this time just to get a little practice with it. The 7 factorials cancel out, the 2 cancels with the 8, leaving a 4, so 9 times 4 is 36. Let's put that here. So we have minus 36 over, well, here we have 9 times 4 times 32. So I'm doing it this way because I'm going to cancel this with this as well. And the answer is going to be negative 1 over 32. In this case, the answer was allowed to not be an integer. It was 1 over 32, but that's not because of the binomial coefficient, okay? The fraction came from the fact that we had a 1/3 here and a 1/2 here. And finally, the final question is also about a constant term, but in this case it's one, again, with variation. It's not asking the straightforward question. Instead, it is saying that something about the constant term and then asking you for the exponent, which was the other version that we hadn't found yet, a question that has the exponent itself as an unknown that you have to find. So before we solve this question, in order to actually understand what he's asking, let's go back to question number 4 and think about that a little bit. He asked us to find the constant term, and the answer was, I don't remember, 5,000 and something, but it was not 0, right? I'm interested in 0 because I see that question 6 is talking about a non-zero constant term. So I'm trying to figure out what's interesting about when it's 0 and when it's not 0. But here's the thing. The exponent in that question was not 15 by chance. It kind of had to be 15 or something similar to 15. It definitely wouldn't work with any sort of number, like 14 wouldn't work, for example. How is that going to have a constant term? It has a bunch of x to the power of 2. It's going to have a constant term only if the x's in the numerator cancel out with the x's in the denominator. And it's going to have quite a few of each one of them because this is a power of 15, right? So it's a repeated multiplication of this binomial over and over again 15 times. So even though we are using the binomial theorem formula for this, for focusing on one term that we're interested in, which is very convenient so that we don't have to do all the distributive that there is, we still can't forget that that big distributive is there. So what is happening in this big multiplication is that in every way possible, we are going along choosing one of these two for each one of the 15 factors, and then we're multiplying those things down here. So for example, if I start by choosing the x to the power of 2 times the 1 over x to the power of 3, well, there is a little bit of cancellation going on here, right? We can cancel this x squared with 2 of these on the bottom and just leaves 1 over x, but that is not a constant term. It still has x in the denominator. So hopefully the next one that we take is x squared. So now we can cancel that remaining x from the denominator with one of these from the numerator, but now it's wrong the other way. Now I have a little bit of x remaining on the numerator. So it's not as easy to get a constant term. In this particular case, things are going to start canceling out. If I have 3 of these and 2 of these, because then I'm going to have 2 times 3, 6x's on the numerator, and 3 times 2, again, 6x's in the denominator. So 6 cancels with 6, and I'm left with a constant term. So every time I have 3 of these to cancel with 2 of these, that makes it constant. But that means I need exactly 5 terms, 3 here and 2 here. And if I do that again, then again those 5 terms cancel out. So in the end, this exponent here, in order for the answer to be interesting, for the problem to be interesting, needs to be a multiple of 5. If it was like 14 over there, then the answer would just be 0 and there would be no point in doing any of the things that we did in that question. So that is the kind of thing that this last question is about. You can't expect the answer to be n needs to be any number that is a multiple of something, instead of just n has to be 12. It's not going to be a fixed answer like that. So in this case, I'm actually going to need 3 of these to cancel 1 of this. So it's 3 of these for each one of this. So it's 4 terms that I need in order for them to cancel out and have a non-zero constant term. So if n is 4, we will be fine. If n is 8, we're also fine. So that is the answer. N needs to be a multiple of 4. I guess that in the question 6, if you happen to have a number that doesn't work, like 14, then when it came to this calculation here, where you're trying to find the value of r, you would find something that doesn't make sense. Like you would find a fractional value for r, which is not the way that the binomial theorem formula works. And that should give you a hint that those terms don't cancel out properly, so there is no constant term in that situation. So the answer should be 0. The constant term is 0 because it's not actually there.